Okay, onward we go to problem 3, which is this one about, hang on, let me find it. Right, it's one about geosynchronous orbit. So, to explain this to you guys, the idea is the satellite in geosynchronous orbit always appears to be above the same spot on Earth. So I'm going to say here's the Earth, and there's our little spot. There's the center of the Earth, more or less. Okay, so here now appears our satellite in geosynchronous orbit. Okay, and this satellite is going to be orbiting around the Earth. Okay, so it's going to be moving that way, let's say. And what we want to do is find where it is, where it has to be, what altitude it has to be at, in order for it to move around the Earth at the same rate that a guy on the surface moves around due to the Earth's rotation. So the Earth is rotating, okay, and it rotates in 24 hours, right? And so the idea is the satellite should circle the Earth in 24 hours so that it's always right above the same spot. So a guy standing there would then always have the satellite directly overhead, no matter how much time passed, because the satellite would be keeping up with him as it goes around. So first of all, it's sort of obvious, I think, but maybe not entirely, that this has to be a spot on the equator, right? The spot that the geosynchronous satellite orbits. Otherwise, it's not going to work. And so what needs to be true is that this satellite has to go around the Earth in the same time it takes this guy to complete one circle around the Earth. And the time that takes is what we call a day. So the period for this geosynchronous satellite is going to have to be 24 hours. Okay, which is, I hear there's a song that uses this in its lyrics, 86,400 seconds. Okay, so, but if you don't know the song, I mean I don't, but if you, oh God, I hate that, let's see. If you don't know the song, just take 24 and multiply it by 60 to get the number of minutes in a day, and then 60 to get the number of seconds in a day, and there you are. Okay, so what's more useful for me, I think, maybe not for you, but for me, is instead of using t, our period, we use omega, which is your angular velocity. And the satellite has to have a certain angular velocity to get it around in 24 hours. And that angular velocity is 2 pi, which is the number of radians in a full revolution, divided by t. Because in a time t, it has to go through 2 pi radians. Okay? So, where can we go there? I guess we can calculate omega, but we'll hold off on that for a second. So here's the point. This satellite now is in geosynchronous orbit, okay, and it's being its centripetal force is being provided by gravity, okay. So Fg there, which means that gravitational force, okay, Fg is the only force acting on it, and that has to be what keeps it in motion. That has to be providing the centripetal force. So we can now use one of our expressions for A from uniform circular motion. The two most commonly used ones are A equals omega squared r and A equals v squared over r. And either one can work, but we've got a direct line to omega, right? We've got omega here, which we can calculate directly from t, so it makes more sense to me to use omega squared. Okay, meanwhile, over here for the gravitational force, we just plug in ye old Newton's universal gravitation law. Okay, so g me times m over the distance between the Earth center and the satellite center squared. Okay, and that equals then m, and this a here becomes omega squared r. And so now, let's see, where does that leave us? Leaves us wanting a different color, of course. We can cancel the m's, and we can take this r here and slop it under there. Let's see, do we want to do that? No, because actually we want to get it for r, we want to get r on one side by itself and everything else on the other side. So what we actually want to do is, and I'm skipping a step here by flipping sides, but r cubed is going to equal, so that's taking this r squared, bringing it over here, but writing that side on the left. That's going to then be, we're going to have our g me over omega squared. Okay, so there you go. And if you really want to, push this out, you can say that you can substitute 2 pi over t for that. So then you can say that r cubed is going to be g me t squared over 4 pi squared. And remember this GME here, this here, GME, we already know from up here. Even though we still don't know the mass of the Earth or capital G by themselves, we do know this product just from looking at, an object falling on the surface. So there we go with that. And I guess I can plug this into the old Google, which also handily acts as a calculator. So 3.98, I'm doing this on my laptop, times the 14th, times 86,400 squared, and then we're going to divide that by 4 times pi squared. Okay, then I want to take all of that and take the cube root, which means raising it to the 1/3 power. And what I get there is that the radius of the orbit is going to be, let's see, 42.2 million meters, which means 42,200, I'll take one more decimal point, 220 kilometers. Now remember, that's the radius of the orbit, so we have to subtract the Earth's radius to get the altitude, which is what the problem asked for. So I think then the altitude for geosynchronous orbit would be this minus 6751, or sorry, 6371, which, oh crap, now I've got to, let's see, 36, 35, 850 kilometers, give or take. Okay, so that's the height of a geosynchronous satellite, which is roughly 5 times the Earth's radius. No, 6 times the Earth, almost 6 times the Earth's radius. Yeah, fascinating stuff. Anyway, that's problem 3.